Welcome. In this session on natural deduction, we'll explore the concept of binding, which is closely related to the concept of scope. Let's recall scope. And the way we defined it in a previous session was that for a quantifier Q, and this is simply a way that we can abbreviate using the for alls and that there exists. For a quantifier Q, the scope of Q in the statement quantify X for a formula is the occurrence of X in phi, and then we had a very important one which was minus the scope of X in, and we'll just abbreviate this, in any quantified, we'll say quantified subformula C of that formula. And one example that we can look at is this. So suppose that what we have is we have for all x, P of x implies there exists an x such that R of x, y is true. And for this, we can quickly write down the parse tree. And the parse tree would begin with for all x, and then this is a material implication, and the antecedent is a predicate of a variable, and the consequent is a quantification, and that quantifier is of a predicate. Sometimes we'll call a predicate that has two arguments a relation, but technically it's still a predicate, and this predicate refers to two variables, one being x and one being y. And in this parse tree, we can see that the scope of this quantifier, the scope of the for all quantifier, is only the left part of the parse tree, and on the right part of the parse tree, it's getting redefined. So that will give us the scope in that example. And a binding is the variable's point of view of scope. So what we'll do is we'll say for binding, we'll say that a variable x in a formula phi is bound, we'll say means that x is within the scope of a quantifier. And we will say a variable x, we'll skip that in a formula, well, we'll write it down in a formula phi is free, means that x is not bound. And let's go through this example quickly. So as we go through this example, what we can see is that here x is bound, and it's bound by the universal quantifier. Here x is bound, and it's bound by this existential quantifier. And here we see y is free, because as we go up the parse tree, we never get to a quantifier that refers to y. So here we'll say that x is bound by this quantifier, this x is bound by this quantifier, and y is a free variable in this entire formula. So here this entire formula is the formula phi that we're looking at. Now, a related concept that we'll need to understand the new rules of deduction for predicate logic is a term t is, and the technical way that we'll write that is free for x in phi. So that's what we're saying. Free for x is the key phrase here. Free for x in phi, we'll say, is defined as substituting t in place of x in phi I'll say results in t being free in phi. So, for example, let's take an example. Here, what we have is our so here, let's take up this little space here. And for example, if we have for all x and then everything that follows is our free, right? Then we cannot substitute y in place of x. And the reason is that if we substitute y, then this substitution is fine, because in this part, this p of x is free for y in x. And if we substitute y in this part, we substitute this, and then we substitute that, and now that y becomes bound. So when we have a term that is free for x, substituting it means that when we do that substitution, the variable, the term that we're putting in, which in our case is almost always a variable, when we substitute that term in, we're still leaving the term free in the formula. So this is a particularly annoying example, because in this example we've redefined this x, and it gets quite messy quite quickly. But basically what that means is that we want to have a variable that is so such a term is and we'll call it a fresh term. So if we introduce a term and the term, when substituted in, doesn't change the binding, then that means that it's a fresh variable, and that's the kind of variable that we're going to use in the proofs in subsequent sessions.